Okay, back to communication. We've learned in those previous videos that we need to be able to communicate the difference between something like this and its enantiomer. So how do we sort of say, as we're naming a compound, which one we're talking about? Well, we came up with a set of rules for that. We're going to go over that here. So we're going to call this naming configurations. Again, when I say configuration, I'm saying, is this sort of the one right-handed or the left-handed? So here are the sort of person-invented rules of how we're going to do this. First, we're going to find the chiral center. So here's the chiral center in 2-butanol. Then we are going to rank the 4 substituents. What's going to be used in the ranking? So the first thing we're going to look at is the size of the atom, just the one atom that's connected to the chiral center. So here I've got oxygen is bigger than carbon, so oxygen gets to be number 1. Hydrogen gets to be the last one, number 4. Here I've got carbon versus carbon, and so just like the card game War, we're going to keep sort of walking it out for the tiebreaker. So here it says most bonds to biggest atom. Here this carbon has another carbon attached to it, this carbon doesn't. So this one wins the fight. So that's number 2 and that's number 3. Okay, so I've got my molecule substituents ranked. Now I want to make sure it's drawn with number 4 at the back. What do I mean by put the number 4 substituent at the back? Well, I can draw it like this, but again, you can get a tetrahedron like this. You can kind of picture that number 4 substituent as like the stem of the flower, right? It's a pretty flower. I can look at it like this. The number of 4 is going back like this. Here, all 3 of these are kind of coming at me the same amount. I can tilt the flower a little bit and get a different perspective. But that's how we should think about this. I want to be kind of orienting myself so that I'm looking at the molecule where the last substituent, number 4, usually a hydrogen, is going away from me like this. And those of you that are gifted with sort of spatial reasoning will get good at this, and you'll be able to like think, okay, if I shrank down and looked at the molecule like this, this is what it would look like. So now the last step is to turn the wheel. So I'm going to turn the number 1 substituent into the number 2 substituent. So again, look at it, put your hands on the big old big rig steering wheel, and if 1 into 2 is left, it's S, and if 1 into 2 is right, it's R. So in this case, if I were to look at the thing and turn 1 into 2, I'd be turning left. Left is S, like sinister from the Latin, right? So left is S, right is R. So this one matches this S, S2 butanol, distinct from R2 butanol. Let's take a look at this with a slightly more complicated molecule. This is menthol, so it's in mint, it's in candy, it's in liquor, it's in all kinds of stuff. So menthol has 3 chiral centers, and so we're going to have to assign each of the 3 R versus S. So let's start with the top one. Top one, we've got 4 carbons, or 3 carbons and 1 hydrogen, so we have to rank those. H is going to be the 4th one, like it usually is. The methyl on the top is going to be number 3 because it's not connected to anything cool on the top end. Here I've got 2 CH2s, and so it's a push, it's a tie. So we go down here, and this side, this is connected to an OH. So this side, so this one wins that battle, and then this one is going to be number 2. I'm luckily already got it drawn, so number 4 is going to the back, so now I just need to turn the big rig wheel. That would be turning the big rig to the right, and so this one is R. Now let's take this carbon. So here I've got oxygen, 2 carbons and a hydrogen. Hydrogen again comes up last. Oxygen comes up first. If I'm comparing the other 2 carbons, CH2 loses out to CH with 2 other carbons connected to it. So this atom is bound to more heavy atoms than this one is. So this one gets number 2, this one gets number 3. Again, number 4 is already, my last substituent is already pointed to the back, so I'm cool there. Turn the big wheel, 1 into 2. Once again, that's going to be R. Finally, we have to look at this carbon here. Right? So here this carbon's got carbon, 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 and hydrogen, and our luck has run out as we don't have the number 4 lowest ranking substituent pointing to the back. It's pointing to the front. Rough. So there are 2 ways that we can kind of solve this problem. I'll go through the long way and then I'll go through the confusing way. First, the long way. Let me just redraw the molecule flipped around. So here's the molecule flipped around. Now it's at the back. Among these carbons, this carbon is bound to an oxygen. That's the biggest atom, right, in our tiebreaker. This carbon's bound to carbons, 2 carbons. This carbon's bound to 1 carbon. So carbon bound to oxygen wins. Carbon bound to 2 carbons in second. Carbon bound to 1 carbon third. So here, again, 1 into 2. S. That's going to be S. So there, I just redrew the molecule completely flipped around to put the S at the back, or to put the lowest one at the back. Once you get enough practice at this, maybe you just say, you know what, I'm just going to do it on this, and then remember that that's the wrong answer, and just flip it at the end. But for now, yes, when you have something with your lowest substituent at the front, you got to redraw it to put it at the back. So this is 1R, 2S, 5R menthol, according to the numbering of the menthol ring. So as I name this, again, if I have a compound with more than 1 chiral center, it's important for me to note which is which. So this is R, this one's S, this one's R. If I wanted to name the enantiomer would just flip all the stereocenters. So if I were to draw the enantiomer, it would be methyl going back, OH going back, isopropyl coming out. So I flip all of the stereocenters, and then I flip all of the configurations down here. So the enantiomer of this RSR would be SRS. Okay, just flip everything. Flipping everything gives you the enantiomer. What if I have some other combination that's not just flipping everything, right? So what if I change 1 or 2 of the stereocenters, but not all of them? These combinations would be diastereomers of the original menthol and diastereomers of each other. All right? Remember, diastereomers are not simply mirror images. They are compounds that have the same atoms and the same connectivity, but they have different shapes. All right? So if I change all the configurations, that's the enantiomer. If I change one or some of them, that's a diastereomer, different shapes. As we go forward, we'll learn about what the kind of physical, measurable differences between diastereomers and enantiomers are.